Welcome to today's class of analog microelectronic circuits. So today is your lecture 5, and today's class we will start with MOSFET structure and operation. So previous 4 classes we spent time to brush up through some of the preliminaries and to understand how we can apply those preliminaries, like how we'll apply KCL, KVL, and such things in the coming classes to deal the course in a better way. I hope I'm audible.
Yes, sir.
Yes, okay, thank you. Right. So I'll start this class by looking at what an electronic device is. So far we discussed a lot of elements like resistors, voltage sources, current sources, and the series parallel combination of those things, right? Now we will start with the electronic device. So what to mean by an electronic device is an electronic component which actually allows the control, which actually controls the flow of current. So such components are generally called as electronic devices. So the components used for controlling the flow of current. Generally, right. Now, again, we classify devices as passive and active devices. Again, when you talk about active devices, this is what an active device basically does. There will be a controlling terminal actually to control the flow of current through that particular device. So if you look at, if I say I want to control the flow of current through any device, that is pointing to something called as 3-terminal devices, right? And if I talk about 3-terminal devices, the one device which comes to your mind is definitely transistor. And I hope you had learned the basics of transistor in your first semester course. Rather, we will start, even though you have done that, we will start from the fundamentals. Now, basically, if I look at a transistor, we can say that it's a 3-terminal device, and for various reasons, like you have used transistors, you may have used even in your PUC as well, right? So now let me start with the classification of transistors. So I can classify transistors in 2 categories as bipolar transistors. We call it as bipolar junction transistors, which we call as BJTs, and the other category is field effect transistors. Right, we call them as FETs. And there are various FETs available, and if I further look down into the categories of FET, we will end up with several FETs, and the prominent ones or the ones we usually discuss are JFETs and MOSFETs. Now, our attention, we will be starting our course with the most popular device, both in discrete and integrated circuit, that is nothing but MOSFET. Right. Now, I hope you all are familiar what a MOSFET is. Can I get responses in the chat box what a MOSFET is exactly? The name of the device. MOSFET stands for?
Metal oxide semiconductor field effect transistor.
Yes, it is metal oxide semiconductor field effect transistor. Yes, thanks Maheshwari. It is metal oxide semiconductor field effect transistor. Yes. I'm reading out Charan Kumar, Prakash, Jessica. Yes, it is a metal oxide semiconductor field effect transistor. Right. Now, if I look at the name itself, I can say that this is basically from the structure of the MOSFET. This tells you what a MOSFET structure is. And the second part, field of effect transistor, is basically the principle of operation. So we will look at both things. We'll start with the structure of a MOSFET, and later we will see how a MOSFET operates. And one more thing I want to list here, probably you would have heard. Even in MOSFET, we generally categorize into two types. One we call as depletion type MOSFET, and the other one we call as enhancement type MOSFET. For our course, especially for amplifiers, we will be looking at the second category, which is enhancement type MOSFET. But depletion type MOSFETs are also widely used in circuits, especially in startup circuits and all. So probably when we study more on integrated circuits, we'll exactly see where some of the applications of even this depletion type MOSFET. Right. So for now, I'll be limiting. We'll be focusing on the structure and operation of an enhancement type MOSFET. And one more thing I just want to note on here, that the basic difference between these two devices, these two type of MOSFETs, depletion type and enhancement type. So can I get a response in chat box, not as an audio? In chat box, can you just tell me what is the difference between this depletion type and enhancement type MOSFET? Any one difference or the main difference? No responses. So whether my audio and video are lagging? All right. Okay. So if at all you see a lag between my audio and video, then please let me know immediately. Right. Yes. So I can see the responses. In enhancement, channel is induced. Yes. Depletion needs GS voltage to turn off. Yes. Yes, that is true. So so generally, just to understand, we say that this depletion type MOSFET is a normally on device. So what does it mean by normally on device? If you look at the structure of the MOSFET, this depletion MOSFET, we will understand that this will have actually a channel. The channel will be there, or normally on device means that the device will carry a current, right? Now enhancement type MOSFET is a normally off device. Normally off device. So I can write here, channel is absent, and we need to we need to apply a voltage to enhance the formation of a channel. So that is the basic difference. One is a normally on device, another one is normally off device, and we will be focusing on this normally off device, which finds a lot of application in discrete as well as integrated circuits. Right. So moving on, the discussion on enhancement type MOSFET. Right. So Let me start with the structure. So as you have given me responses like MOSFET is nothing but a metal oxide semiconductor. Hello. How is it now? Hello. Am I audible? All right. So if there is a lag, please let me know. Yes, yes. Thank you. Right. So we start with the semiconductor layer. Right. And generally we call this semiconductor as substrate. And this substrate acts as the place over which I can actually fabricate my device. So here I am looking at a MOSFET device, and this substrate acts as the base layer where we fabricate the entire device. So for that reason, we call the substrate even as, otherwise the substrate is called as bulk, or we call this as body also. Right. Now we are talking about semiconductor devices. So when I start with a semiconductor substrate, the substrate can be of two types. Either the substrate can be of P type or the substrate can be of N type. Right. So depending on that, again, your enhancement type MOSFETs are of two types. One is a P MOSFET and another one is an N MOSFET. But we'll see how we name that. So for the time being, I'll start with this as a P substrate. So our starting base layer is a P substrate, and we call the substrate as body or bulk of the device. Now, on the substrate, the device is built. So as we have seen the other two layers, there is a metal layer and there is an oxide layer. So even before that, I want to define two more layers within this substrate. All right. Yeah. So I'll be before defining that, let me mark the oxide layer. So this is your oxide layer, and on the top of the oxide layer, we have another metal layer. Right. So here I'll mark this is the oxide layer, and this oxide is typically something called as silicon dioxide, SiO2. And the top, what you have is your metal layer. This is generally, in previous days, we were using metals like aluminum, but these days, over more than past 10 years, we are using something called as polysilicon, which is a highly conductive material. And there are new materials are being used for gate for various reasons. So as we progress this course, we will see why new materials are required. Especially in your VLSI design course, you will study more detail about the different gate materials and the reasons for using that. So For this course, I'll be limiting this as we have a metal layer. Oh, there is background noise. All right. One of you can unmute and just let me know. How is it now? Is it better?
Yes, sir.
Yeah, so there are a lot of background noise before.
Yes, sir. So there was a lot of noise.
Huh?
Like someone is banging the table, it was going on like this. So.
Oh, all right. Okay. Yeah. So now is it fine?
Yes, sir.
Okay. Okay. Yeah. Fine. Yeah. So this is here the structure. You have a metal layer, you have an oxide layer, and you have a substrate or body or bulk layer. Right. So these are the three layers. Now, as I mentioned, this is a three-terminal device, and we have actually. So this is actually one. This is one terminal. We call this as metal, and this is another terminal. We call this as body. Right. This is body, and this is your metal terminal. Now, this will not exact. This is not a three-terminal device. Now you can see only two terminals. Now, for a MOSFET, so to complete the structure of MOSFET, in fact, you have a metal, oxide, and semiconductor layer. We have to define two more regions on the P substrate. That will really help in the current conduction or control between those two terminals, or current will be definitely current will be flowing through those two terminals, because now you can see that your metal layer is actually insulated from this P substrate, right? So this is the green color is your metal layer, and that is insulated from your P substrate. So definitely I can say there is no current flowing into this, right? The current flowing into into the semiconductor or into the substrate is definitely zero, because there is an insulate, or your metal layer is in fact separated from the rest of the device, right? So now I am taking you to the complete structure. As you know, we have metal oxide semiconductor, but we have to define two more regions on the substrate. That is what we are seeing here. Yeah, there are two more regions. Those regions we define as N plus regions, and those two N plus regions are defined on the P substrate itself. So let me tell you one difference. So whenever I write something as N plus, the meaning is it is a heavily doped region. Right. So N region, we know that whenever an intrinsic semiconductor is doped with an N-type impurity, we will get an N region. Now, if that impurity is heavily doped, we usually mark it using N plus. Similarly, if it is lightly doped, we mark it as N minus. Right. So in the previously mentioned the substrate or the bulk or the body, we are defining two N plus regions on both sides. And now you can see your metal layer, an oxide layer, and the semiconductor layer with these two additional regions defined on the substrate. And now we will not exactly see how this device is fabricated. So fabrication in the sense, we will start with the substrate. On the substrate, we will define the regions for regions 2 N plus regions. So there are a lot of process fabrication steps in order to arrive at this structure. So we will not look at those processes in detail. Those processes will be dealt in the course VLSI design when in your fifth semester in very detail. The different fabrication steps you will be dealing there. Now we will be looking at the structure. We will understand the operation, and then we will take the structure. Then we will take this device in order to build circuits that is useful. Actually, that makes our lives easier, right? So previously defined body terminal I defined. Now the metal layer is defined as, or the metal layer is called as gate of the device, and the two regions what I defined on the P substrate as n plus regions we call as source. So even though I started that this is a 3-terminal device, in fact there are 4 terminals for the device, and the 4th terminal usually we neglect, or usually we will not specify explicitly is the body terminal. And there is a reason for that, why we generally call MOSFET as a 3-terminal device even though it is having 4 terminals. I'll come to that reason now. So what you are seeing here is actually a cross-section view of MOSFET. Now you can see on the left side here, you will see the MOSFET, complete MOSFET. You can see the various dimensions of the MOSFET. So generally, we define MOSFET. There are 3 dimensions. One is width of MOSFET, which is marked here. The second is length. And so that is marked here. And finally, one more dimension is thickness of oxide layer. That is actually marked here. Right. So these are the 3 dimensions. So we call this as W, this as L, and this as Tox. Right. Now, even though I wrote here as width of MOSFET or length of MOSFET, in fact, the width and length are defined for the channel. So we will come to that a little later. Right. So for precisely, maybe I'll write it that now here now itself. This is width of channel. This is length of channel, and the third dimension is thickness of the oxide layer or oxide layer thickness. Right. So this is the structure of MOSFET. You have a P substrate. On P substrate, there are 2 heavily doped N regions, and these N regions are actually built on this P substrate through a fabrication process known as diffusion. And after that, we will deposit this oxide layer, and on the top of oxide layer you have metal layer. So metal contacts are taken from source. Metal contacts are taken from all the 3 regions, this N plus region, the second N plus region, and also from the top of the oxide layer. Now we call the other 3 terminals as, this terminal is called as, one terminal is called as source, and the other terminal is called as drain. And the middle terminal, which is taken from the top of the oxide layer, is called as gate. So from the name itself, we will get to know that the terminal is defined as gate because basically that terminal controls the current flow between these 2 terminals. So we are interested in the current flow between the terminals source and drain, and the control is in fact activated, or control is done by the 3rd terminal here, gate. So if a current is flowing from source to drain, we generally call that current as I, and with the, maybe we'll come to the notations little later. So this is the structure of a MOSFET. So any doubts so far in the structure?
No, sir.
All right. Probably you would have seen the structure many times before also, right? Now, one very important thing is, as I mentioned, even though this is a 4-terminal device, we generally consider this as 3-terminal device for one reason. The reason is the substrate, what I told before as the base layer or the device, the entire device is fabricated on this substrate or this bulk or body, and generally this acts as a support also for the device. Now, since gate is controlling the current flow between source and drain, right? So since this gate terminal, since this is controlling the current flow, what I want between the source and drain, generally we are not expecting any current flow between these junctions, right? You can see that on a P substrate there are two N plus regions formed. That means definitely there are two PN junctions here. So in the structure you can see that there are two PN junctions. These two PN junctions are formed between source and body and drain and body, right? So I can consider this as a PN junction. Again, you can see another PN junction here. But we are not interested in a current flow between these two PN. Reverse bias. If we are not expecting any current, these two PN junctions should be always in reverse bias. Now, what is the easiest way to keep these two junctions in reverse bias? So body is a P substrate, and the other two source and drain are N region. So that is why this forms a PN junction. So generally, what we do is we connect this body terminal to the least potential available in a circuit, to the least potential. And this is true for a P substrate. So if your substrate is P, we will connect the body to the least potential. Say if the least potential is ground, body should be connected to ground. So what will happen if body is connected? Why I am specifying, yes, body at 0 volt. Yes, Krishna, true. So if your body is connected to the least potential available, then this PN junction between the body and source and body and drain will not be forward biased. If these two junctions are forward biased, if these two junctions are not forward biased, we can say that there will not be any current here and there will not be any current flowing in these junctions, because those currents are not desired currents, because we are looking at the current flow between source and drain and we want to have a control of current flowing between the two terminals. So now these two junctions should be always reverse biased, right? So that is for that reason we should understand that P substrate, if the body is P substrate, we have to connect that to the least potential, right? Now if the body is P substrate, how do we name this MOSFET? If body is P substrate, we call this MOSFET as actually N MOSFET. We call this as N MOSFET because current is flowing between source and drain. Those are N layers, and definitely that will be the current flow is will happen through a channel which is formed between source and drain. That also will be an N type channel. We will see how the channel is formed, all those details. So NMOS substrate will be P, and in that case body will be connected to least potential. So why I said that least potential instead of telling body should be connected to 0? If there will be certain circuits which works with dual power supplies, where it works with a plus VCC and it works with a minus VEE. Then there are even if you would have come across certain devices, certain circuits, ICs. Many ICs work with plus and minus voltages. So in that case, body should be connected to the least potential, means body should be connected to minus VE. So in general, we can say that body should be connected to 0 if the least potential available is 0. That is the case of an N MOSFET. Now, if you have a P MOSFET, the meaning is the starting substrate is an N substrate, and in that case, body should be connected to highest potential. Again, for the reason that the PN junction formed between the source and body and drain and body should be cut off. There should not be any current flow between those two junctions. Right. I hope this is clear how the body should be connected. Now, So if in a circuit, if you have multiple power supplies available, yeah, so generally I told body should be connected to the least potential. Now, one easiest way than this is, if possible, if you can short the source and body. If I'm shorting the source and body terminal together like this, what will happen? You have a PN junction. So you have a PN junction here, right? And you are trying to actually short. That means there is 0 volt. Will be reverse biased. If it is reverse biased, there will not be any current flow, right? That also is possible. So if we have multiple supply voltages available, you can do that. If that is not there, generally we will short the source terminal to the body terminal, right? So since body is shorted to source, and since that is possible, we consider this as a 3-terminal device. So when we say MOSFET as a 3-terminal device, it is understood that body is internally connected to the source terminal. So when you come to AMC lab, analog microelectronics lab, you will see MOSFETs in your lab. So it will be having only 3 terminals. That means the 4th clear? Any doubt?
Your voice broke.
So the last sentence.
My voice is breaking.
The last sentence, what you just told,
Last sentence was not audible.
Oh, all right. Oh, sorry. So I was. Did you hear what I meant by drawing this diode and 0 volt across
Yes,
that?
sir. We are till AMC lab.
Yeah. So what? Yeah. So what I was telling is, your body terminal will be shorted or.
Sir, you are not audible again.
Hello. Hello.
Yes, sir.
Yes, sir.
I'm very sorry. I don't
Yes,
know.
sir.
All right. Yeah. Not audible. Now is it clear now?
Yes, sir.
Yes, sir. Now clear.
Okay. I'm very sorry for the internet connectivity issues. Right. Okay. Going further, we'll be so in circuits.
Your voice breaking.
All right. Okay. But now you are getting a lot of other background noise, right?
Yes, sir. Yes, sir.
How about now? Still the background noise exists or it is not there?
I think now it's fine, sir.
It is fine.
Yes, sir.
Okay. I'm very sorry for all these online glitches. Right. but please intimate me immediately when there are such issues happening. Right. Thank you. I hope I can proceed further.
Yes, sir.
Yes, sir.
Okay. Yeah. Yeah. So now let us look at the symbol of MOSFET. So again, for this, probably you would have seen symbols of MOSFET. So as we discussed now, there are 4 terminals. One is gate, another one is source, drain, and body. These are the 4 terminals of the MOSFET. Now, we generally draw the symbol of MOSFET with this as gate, and this is your gate metal layer. Now we know that gate or this metal layer is isolated from the rest of the device. So we in fact give a small space there. And then we have 3 terminals. One is drain, one is body, and one is source. So we mark it as 3 different terminals like this. This forms your drain terminal, this forms your source terminal, and this is your body terminal. Right. Now, and you will probably see this also, an arrow mark in the body to show that indicates that. So generally arrow mark in a device shows that is the actual flow, the current flows in that direction, right? But in this case we know that there is no current flow. We are not in fact trying to get any current from body to the source or body to the drain, right? But still to show that it is a p substrate, and if that junction is forward bias, the current flow will be in that direction. That is the meaning of this symbol. Now, if you look at the breaks here, you can see that drain, body, and source terminal is actually shown as isolated, right? So this is to represent that this is enhancement MOSFET, meaning there are no connection between drain and source when the device is off or when we are not giving any potential. So naturally it is a off device. So current cannot flow between drain and source. That is shown by the break in the symbol. But we know that when a potential is applied, a channel will be formed and current can flow from drain to source. So generally we will not use this symbol for the reason we should have more patience actually to draw a circuit, draw a big circuit, and in that if there are 10 MOSFETs, we should actually spend time in drawing all these details there. So generally in circuits, we modify the symbol as this one, and this is the general, the widely used symbol of MOSFET in analog circuits, where this shows the gate, this shows the drain, and this shows the source terminal with an arrow mark shown at the source, meaning current is actually flowing from drain to source in this direction, and this is the direction of the current, right? And this even we use this for enhancement MOSFET with the understanding that whenever a voltage is applied, a channel will be formed and the current conduction or current will definitely flow through this. Now, body can be shown as the 4th terminal, and as I mentioned, if body is tied to source, it is in this form. Body will be connected to the source like this, or even we can actually omit. No need to use also the body terminal. That also will state that body is actually connected to the source terminal. So this is body, this is source, this is gate, and this is drain, right? So this is the symbol of, so what MOSFET is this? This is an N channel enhancement type MOSFET. N channel enhancement type MOSFET, right? So any doubts so far?
No, sir.
Any doubts from others?
No, sir.
Okay, all right. So let us move on. So we have defined the basic structure of MOSFET. We have looked at the different terminals, and we have looked at the symbol. Now let us move into the operation of this MOSFET device. So metal oxide semiconductor is a structure. We have looked at that in detail. Now we will see the operation of this. So when I say operation, operation of the device means how current flows through this device, and how a control is ensured on the current flow between the terminals, right? So to understand that, we should first understand how a channel is formed, because we know that from the symbol itself, a current cannot flow easily, or a current cannot flow when your device is a normally off device. So in order to make sure that a current flow, your first job is actually to create a channel, right? So we will start our study of operation of the MOSFET with different headings. First, we'll understand how a channel is formed in a device, right? Now so before that, let me tell certain few device physics to make our explanation more easy. We know that there are two type of semiconductors, p-type and n-type semiconductor, right? In p-type semiconductor, the majority charge carriers are holes, and in n-type semiconductor, the majority charge carriers are electrons, right? Now in general, any electronic device, if you see, there is something called as space charge neutrality. That means the sum of total positive charges will be equal to sum of total negative charges. We call this as charge neutrality equation, right? And for every electron in a device, for every electron in a semiconductor, there will be a positive ion associated. That means basically, you know that when an electron is made free from an atom, the atom becomes an ion, and we call that, and that ion will be a positively charged ion. Maybe these things you would have even studied in your chemistry in your 10th or in your PUC. And each hole will have a negative ion. We call this as immobile ions. These are immobiles. Ions are immobile. Atoms are immobile. Only electrons can move, right? So these things you keep in mind. This may help us in while we explain the operation of this MOSFET, right? So let us start with the channel formation. So in order to understand that, let me, before going to that, let me start with two parallel metal plates, and assume that there are two parallel metal plates, and assume that there is some dielectric in between those two metal plates. So this dielectric can be vacuum, or this can be an oxide layer, or whatever it is. So if there are two metal layers, and if you apply a potential in this form, what will happen? So to this side, since it is connected to the positive of the battery, I will have positive charges deposited here, and to the other side, negative charges will be induced. Right. This is the action of a parallel plate capacitor. So when positive charges are deposited on one side of the metal plate, on the other side, the negative charges will be induced. Right. This is the action of a parallel plate capacitor. The similar action can be taken to understand the operation of a MOSFET. So even in MOSFET, you can see a metal, an oxide layer, and another layer which is conductive. So here these two are conductive layers. This layer and these two are conductive layers. In between there is a dielectric. So if you look at MOSFET also you can see that so these are the N plus layers, and this is the P substrate. Right. And here is the dielectric. And the top of the dielectric there is metal layer. So this is your gate. I'm using only one color here. All these are the different terminals of the MOSFET. Right. Now initially, so let us understand one by one. Let us see how a channel is formed. So at that time I'm not looking at the two terminals, source and drain. So what I will do is I will make sure that the source is connected to ground, drain is also connected to ground. In fact, body, as I mentioned before, body or the bulk of the device also can be shorted to source. Both are at same potential. There is no current flow in this PN junction. And now I am applying a positive voltage to gate. So when I say I am applying a positive voltage, I am applying that voltage with respect to bulk. Sorry, are you guys with me?
Yes, sir.
Oh, I totally forgot. I was into this explanation of the structure and I forgot that you guys are there. I'm very sorry. So are you guys with me? Are you following what I'm doing here?
Yes, sir.
Or you have other tabs opened in your system? No, right? Yeah, I hope all are listening to this. Yes, thank you. Yeah, so to start the understanding of to understand the operation of this, so what I'm doing is I'm not disturbing source and drain terminals as of now. I assume that both are at zero potential. Again, the body terminal is also connected to the same potential of that of source, or in fact your body and source there is no bias and those junctions are reverse bias. Not only this junction is also, both junctions are reverse bias now. And I'm applying a positive voltage to gate. So when I say I'm applying a positive voltage to gate, I'm applying that with respect to bulk or the 0 volt. With respect to the ground connection here, I'm applying a positive voltage. And I know that what happens if I apply a positive voltage, positive charges will be coming on this metal plate. And the similar parallel capacitive action will take place, and negative charges will be induced in the other conductive layer of this parallel plate. Now if I look at this structure, the other conductive plate is nothing but a semiconductor, right? It is not a conductor, it is not a metal, but it is a semiconductor. Now when you apply positive charges, okay, let us start not with positive charges for your understanding. Let me start by applying, say I am applying a negative voltage. So I am applying VG, a negative voltage. Right. So I am applying a negative voltage. So these are negative charges. And on the other side, what you can see is a P substrate. As we discussed, P substrate is having majority carriers as holes, which are positively charged. So what will happen under this condition? If you're applying a negative voltage on the gate, what will happen? Your P substrate is having majority carriers as holes, and those holes will be actually attracted towards this, or this negative charges will in fact create in the sense it'll attract those negative charges will induce positive charges here. Positive charges are nothing but the electrons, sorry, the holes, and these holes are freely available in this P substrate, right? So what happened here, when you applied a negative charge on the gate, so again you are applying negative charge to the gate with respect to body, so your VGB or yeah, we'll come to that. So it is negative with respect to the ground, so you are applying a negative voltage in fact. So a VG negative is actually leading to what is happening. The holes in the semiconductor is moving and it is accumulating beneath the gate region, right? So this we call as accumulation of holes. So why is this happening? Accumulation of holes are happening in the region beneath the gate because of the application of negative voltage to the gate, right? Now we call this, so generally a potential difference is what we are creating, not we cannot have only a single terminal. We can only create a potential difference. Now since it is a potential difference, we have to refer this with respect to one more terminal. So generally we write this as source, for the reason that source is the terminal which is connected to the body for most of the time, and source is generally at a low potential. Now when you say VGS is negative, what is the meaning? VG minus VS is a negative voltage, right? When I write VGS as negative, VG minus VS is negative. So if your VS is 0, your VG has to be a negative voltage. Then only the result will you will get this as a negative voltage, right? I hope this is clear. Now when your VGS is negative, what happens to a MOSFET structure is holes will be accumulated in the region beneath the gate. Now I'll wind up with this. So as you increase this voltage VGS from negative to positive, so as that means if I change this voltage VGS from negative to a positive voltage, what will happen? When I change this from negative to positive, this will change to positive, this will be positive. Now a positive voltage is applied to one side of a parallel plate. Negative charge.
Sir, your voice is breaking.
Oh, still breaking. Hello. Is it good now?
It's fine, sir.
Okay, maybe okay. So since it is time, I'll wind up with this. So we'll continue this in the next class. The operation from like how we will apply VGS positive voltage and how we will go further, right? So one thing, yeah. Let me just stop this recording and we'll discuss.